Hello. In this video I will show you the behavior of what a pointer is doing. First some slides and then I'll show the same behavior in the Kyle example that you can watch back if you want to. Okay, well, in our real world we have several different kinds of CPUs or microcontrollers. In the early days we only had 8-bit CPUs which only handled 8-bit data basically, and at least they stored data in memory as bytes, so 8-bit values, and I have an example here. So assume we have some memory, we have 8 memory locations here. We start at hexadecimal 100 and then an 8-bit CPU would store its 8-bit data over there in order in memory. Then we got some bigger CPUs that could handle 16-bit at a time, and what they did was, of course, instead of storing byte data, they stored 2 bytes of data resulting in 16 bits. And basically if you look at the memory and how the addresses are pointing to the data, we see here that every location is pointed to, and then the address is incremented by 1 every time. And on a 16-bit CPU you see that we have 2 bytes on one memory address, 2 bytes on the next, 2 bytes on the next again, and that basically means that a 6-bit CPU only has even memory addresses. So the first 2 bytes are located at address 100, the next 2 at 102, and then 104, etc. So every time 16 bits are taken, they are taken from an even memory address. Well, even later we got 32-bit CPUs, and in your PC you already have 64 and so on. And there the same principle applies. So it stores 4 bytes on a memory location, 32 bits, and they are all stored at a byte boundary, let's call it like that, which means that the first one in this case is stored at address 100, and the second one is stored at 104, and then the next one 108, etc. So here we have 4 bytes connected together. Here we have 2, and there we have 1. But the addressing scheme is still the same. If we look at here, this is address 100, 101, 102. So at 102 we have here 56, at 102 we have 56 here, and at 102 we have 56 there. So that's no difference between all the kind of CPUs. Well, let's now look at pointers. I have an 8-bit pointer, a 16-bit pointer, and a 32-bit pointer. And they all point at a memory location. I should point it over here, but with the arrow mean that it's pointing at 104, and this arrow points at 100. If we increment the pointer that was pointing there, it will go 1 up. So it increments from 106 to 107. If I look at the 16-bit pointer, when it points at 104 and I increment it, it points at 106, because it has to make a step of 16 bits, so 2 bytes. So it should step from here to there. Same for a 32-bit pointer. When it points at 100 and I increment it by 1, it now points to 104, because it's pointing to a 32-bit number. So it skips 4 bytes here, and it skips 2 bytes over there, or 2 address locations. Okay. So that's what you see happening here. This points from one to that one. And if I'm now using in a 32-bit environment, so this is 32-bit memory location, and I have a 16-bit pointer pointing to 104, when I increment this one, it will point to that, of course, as I explained. And the same for an 8-bit pointer. When it points to here and I increment it, it points to there. And when I increment it again, it points to the next one and to the next one. So you see some kind of addressing, let's call it like that. Okay, that's regarding the presentation. And I also made an example for you in Kyle. Well, what's happening here, I have two variables, A and B, with the same values as in the presentation. That's not exactly the same, as you will see. And I have the memory here also. Well, I see that the value of A is stored in these first 4 bytes, and the value of B is stored here. And the thing that you will notice is that the order, this is the lowest address and then it's counting up, that the order of the bytes here is inverted when we look here. We start here at 1, 2, 3, 4, and here we are going from 7, 8, 5, 6, etc. Well, this is because our CPU stores bytes in a reversed order, but we can ignore that, but it's you can see also what's happening then later in the program. So I made a watch window, and what did I do? I created a pointer to a 30-bit number, 16-bit number and an 8-bit number, and some variables that are still 32-bit, so that everything can be contained. Now, as you know, we should first initialize our pointers. So I point them all to A in this case. We see that A is at 2004, which we show also here in memory. And we see that all the pointers point to A. Sorry. And of course, M and O don't have values. And when I expand them here, you see that the 32-bit pointer sees everything of A, and the 16-bit pointer only sees 5, 6, 7 and 8, so it sees the last part of the 32-bit number, and it's logical because it's inverted, so it points to those two, and the character points to 7, 8, which is of course only the byte over there, so that's okay. And because the pointer only looks at the type it's pointing to, so this points to 32-bit, that to 16-bit and that to 8-bit, we see if I run until there that M has a value of the complete value of A, N only has 16 bits of A, and O only has 1 byte of the value. And if we now increment all these pointers, we see that this is incremented by 4, so it's pointing really at that location, 4, 5, 6, 7, 8, so it points to B. And you can see the value shown here is the value of B over there. But the 16-bit pointer now is only incremented by 2 and now points to the other half of A. So we now see instead of, what was it, 5, 6, 7, 8, it now points to 1, 2, 3, 4, so this half. And for the character pointer that only points to 16-bit, you see that it now has shifted from pointing to 7, 8 to 5, 6. And of course, if I now run until the end, you see that also the values are updated. So M is the value of A, N is the part of A, it points to a value of B is M, sorry, N points to the part of A that the pointer points to here, and O has the byte that the pointer points to. So this is a little bit of explanation how a pointer behaves. So the data type of the pointer is only seeing what you defined. So 32-bit pointer points to values that are 32-bit long, and when you get a value from it, it will take 32 bits. The 16-bit pointer will only get 16 bits, and the character 8-bit pointer only 8 bits. And the same, of course, applies for storing information. Let's do that just very quickly. And I say, okay, store where 8-bit pointer points to, store it with a value of hexadecimal 33, for instance. I build it, run it. I run to there. The same. Well, it points to, what did we see? It points to 5.6 in A. That also show A here. So this pointer points to 5.6 here, and now I replace it by storing 3.3 at that location, and you see that 5.6 is changed in 3.3 over here. Well, that's about it. Pointers and how they behave. Thank you for watching, and until the next video.